Iniciei.
Good morning, everyone. I'm Professor Aldo Zarbin, former president of Brazilian Chemical Society, and I'm honored to be the coordinator of this webinar on behalf of the SBQ. I'd like to acknowledge our president, Professor Romeu Cardoso Rocha Filho, for this kind invitation, and of course, acknowledge the speaker of this morning, Dr. John Warner, for accepting our invitation, for taking the time to speak a little bit with us. It would take a lot more time than I have to properly introduce Dr. Warner, John. However, I could summarize his vast curriculum in one sentence. He is one of the co-founders of the field of green chemistry, co-authoring the defining text and articulating the 12 principles of green chemistry with Paul Anastas. John received his bachelor in chemistry from the University of Massachusetts in Boston and his PhD in chemistry from Princeton University. After working at the Polaroid Corporation for nearly 10 years, he then served as tenured full professor at the University of Massachusetts in Boston and Lowell. In 2007, he founded the Warner Babcock Institute for Green Chemistry with Jim Babcock, which is a research organization developing green chemistry technologies. He now advises several international organizations and in 2020 began working with the Zymergen Corporation. Nowadays, John Warner is a Senior Vice President of Chemistry and Distinguished Research Fellow at the Zymergen Corporation, where he's helping to design and create commercial technologies inspired from nature, consistent with the principles of green chemistry. With over 300 patents, he has invented solutions for dozens of multinational corporations. His inventions have also served as the basis for several new companies. John Warner received the prestigious awards on the different fronts he works, as academic, as industrial chemistry, as inventor, and as contributor on USA governmental chemical policy. Just to mention one example, he was awarded the Presidential Awards for Excellence in Science, Mathematics, and Engineering Mentoring by the President George Bush and National Institute Foundation in 2004. John Warner was named by ICA Services as one of the most influential people impacting the global chemical industries. In 2011, he was elected a Fellow of the American Chemical Society and named one of the 25 visionaries changing the world by Whitney Reader. He serves as a distinguished professor of green chemistry at Monash University in Australia and as the global chair for the Center for Sustainable and Circular Technologies at the University of Bath. And in 2017, the German Ministry of Economic Affairs and the Technical University of Berlin announced the name of the John Warner Center for Green Chemistry Startups in his honor. So, John, please, thanks again, and the virtual stage is yours.
Thank you very much. It's my honor to be asked to speak with you and share a subject that I'm quite passionate about. So thank you very much. I appreciate the opportunity. I'm going to try to share my screen. Please let me know if I've done this correctly. Am I showing my first slide? Good. Thank you very much. It's an honor and a pleasure to be asked to speak with you. I want to begin by saying, a lot of people come in, they sound like they know all the answers to all the questions and everything. I want to say, I don't claim to have any answers to the universe. I don't claim to have some gifted insight. I have been a professional chemist for almost 40 years. I've come to look at the world in a certain way, and I'm going to share that with you. But if I sound like, he thinks, so much, I am not claiming to be correct. What I'm sharing with you is what works for me. And if it works for you, that's good. If it doesn't, we can have a conversation. I spent the first 10 years of my professional life as an industrial chemist. Then I spent the next 12, 13 years of my life as an academic. Then I spent the next 12, 13 years as an entrepreneur, starting 5 or 6 companies and inventing things. And over the past 35 years, I've worked with many governments with chemicals policy. So I've had the opportunity to see how we do chemistry, how we teach chemistry, how we invent chemistry, and how we manage chemistry. And if we're going to have a truly sustainable future for our children and our grandchildren and further generations, all of these must look at how they interact with each other. It's not going to be a solution within one, it's going to be in many. But of course, there are so many approaches. You know, there's cradle to cradle, there's national resilience, there's natural capitalism, circular economy, responsible care, limits to growth, biomimicry, the UN SDGs, the European Green Deal, Alliance to End Plastic Waste, and green chemistry. To me, what's most important, I become very sad when someone says, oh, this is the correct way and this is the incorrect way. All of these approaches are wonderful. All of these approaches are important. We are all different human beings. And if one of these approaches works for one of us, then that's the approach that they should embrace. There doesn't have to be one that is the best or one that is superior. They're all different. And so what we need to do is not look at how they're different, but how they share and work together. And so when I talk about green chemistry, I am not suggesting that green chemistry is somehow better or more important. To me, green chemistry is the part of sustainability that chemists participate in. That's it. So you open up the newspaper, you turn on the radio, you look on the internet, and you hear about all this terrible news, people, cancer, endocrine disruption, and all this stuff. It's like, who in their right mind would ever want to be a chemist these days? There's so much bad news. It's almost like, I don't know, in Brazil, do you have whack-a-mole, this game in which a little creature comes up and you hit it and another one comes up and it comes faster and faster and faster and faster? Well, the American Chemical Society, the mascot of the American Chemical Society, is in fact a mole. And we, in chemistry, we play whack-a-mole. We hear about climate change, whack. We hear about bisphenol A, whack. We hear about PFAS, whack. We hear about nanoparticles, whack. We hear about ocean plastics, whack. And these issues, they come so fast that we don't have time to really understand them. Are they serious? Or are they just crazy? We don't really know. And if we chemists, if we people who have been trained to understand the mechanisms of molecules, if we're confused, can you imagine what the rest of the world that doesn't have chemistry training is doing? And so there's a lot of confusion when it comes to things that could potentially hurt us. Okay, and what we can't do, and what is very popular these days, but we can't do, we can't despair. We can't go, oh my God, everything is terrible, we're all gonna die, everything is bad. This is not gonna get us anywhere. We have to be positive. We have to show, okay, there are some problems, but here is the correct path where we can solve some problems. And so we can't despair, we must be hopeful. Okay, and so let's accept that there may be some red dyes out there that cause cancer. Let's accept that there may be some additives in plastics that cause birth defects. Let's accept that there may be monomers in polymers that are endocrine disruptors. One of the things that, we ask all these questions, is this toxic? Is this dangerous? Is this hurtful? But I wonder, are we asking the right questions? Maybe instead of asking, is this toxic? Is this dangerous? A more fundamental question would be, well, no one wants to make a red dye that causes cancer. Nobody wants to make an additive in the plastic that causes birth defects. If nobody wants this, well, then how does it happen? So maybe instead of looking at how we make molecules, we should consider, how do we train chemists? Okay, now I'm not a historian, I'm not a sociologist, I can't talk about the history of chemistry. I'm a chemist, so maybe there's something in my story as I became a chemist that is useful to look at this. Okay, so I'm not some child who, when he was very young, dreamed of chemistry. I did not have a chemistry set when I was young. I was not into science in any way. I'm from a city in Massachusetts, the United States, called Quincy, just south of Boston. Quincy, Massachusetts, actually is the city where two presidents of the United States, John Adams and John Quincy Adams, are from. And in fact, my hero, the greatest chemist who ever lived, in my opinion, Robert Burns Woodward, R.B. Woodward, is actually from Quincy. From the same city. He actually went to the same high school that I went to, but I grew up never hearing about him. I did not know that this man existed. I come from a huge Sicilian German family. I had 42 cousins within a 5-mile radius growing up. And we were all carpenters, plumbers, electricians. We didn't know about college. We didn't know about university. We would just, we worked in the trades. And when so this high school, and although I took chemistry in my high school in the same classroom that a Nobel laureate, Robert Burns Woodward, was in, I never heard of him. But my friends, when I was graduating, they were saying, oh, I want to go to college. I want to go. And so I decided, well, maybe I'll go to college. And I told my parents. My mother was sad because we could not afford going to university. My father was mad. My older brothers had good jobs. Why would I not just go get a good job? So I agreed to work full-time in the construction industry, and I paid my own university. I went to university, and I went to the University of Massachusetts, Boston. But what horrified my family, worse than the fact that I was going to university, was what I went to university for. You see, I had no interest in science. I was a musician. I went to the university as a music major, but I played in a band. And the band that I played in, the name of it was, wait for it, The Elements. This had nothing to do with carbon, hydrogen, nitrogen. It's a Rubik's Cube, a glass balls. It was the late 70s. We kind of sounded like the band The Cars, if you know them. Better lyrics, okay? Things were going really well. You know, we had a recording contract. We were recording in the same studio as the band Jay Giles. Things were going really, really well. When disaster hit, and the drummer of the band, my good friend, ended up getting leukemia. And over the course of 6 months, he died. And all of a sudden, my life is upside down. Everything about my life is about music. And my friend, he passes away, and I'm saying, what am I going to do? Now, at the University of Massachusetts, although I was a music major, I had to take other courses. I had to take a math class. I had to take a history class. I had to take a science class. Oh my goodness, I had to take a science class. I kind of like biology. I thought that genetics, mitosis, meiosis, that was kind of cool. And I kind of like physics, astronomy, and subatomic particles and quarks. And so I'm saying, oh, should I take biology? Should I take physics? Should I take biology? Should I take physics? And finally, because I had to make a decision, I said, I'll take chemistry, because I saw it as halfway between biology and physics. So I could do a little biology, a little bit of physics, and I'll take chemistry. It's just one course. What do I care? And so I took chemistry, not because of any particular interest, but because I had to take a science class. And so I'm in the teaching laboratory for chemistry, and a professor one day comes walking into the classroom, Professor Jean-Pierre Anselme. He looks at me. I'm a music major. He walks right by me, and he looks at the student next to me, who's a chemistry major, and he says to the student next to me, would you like to do research? Because everything was happening in my life, my friend had just passed away, I'm trying to decide what to do. Just in a moment of inspiration, I said, can I come? And I followed them into the research lab. And when I got into the research lab, my whole life changed. All the time, I thought that there were two types of people. There were artists and there were scientists. And because I was marginally okay at music, I was an artist. I'm not a scientist. But when I realized that scientists created, scientists designed, scientists invented, oh my goodness, I realized I had it wrong, that the word creativity has nothing to do with art and science. It's something much more human. And so I said, I bet the same neurons that go in your brain to design a molecule are the same things that help you compose a piece of music on a piano. And so I fell in love with chemistry. And next thing you know, instead of spending 40, 50, 60 hours a week playing music, I started spending 40, 50, 60 hours a week in a chemistry lab. By the time I was 19 years old, I published 5 papers in journals. In fact, in the city of Boston, this magazine called Celebrity Magazine put me on the cover with Boy George. Now, if that's not a claim to fame, it's really funny. They called me up. They said, John, we think you're Boston's best and brightest college graduate. We want to do a story about you. And I said, I don't want the attention. No, thank you. And so I hung up the phone. I said, no. And so the next morning, I go into my lab. Remember, I'm a researcher, but I still work in a construction company. So I'm not shaven. I'm wearing a flannel shirt. And the chancellor of the university comes and bangs on the door and says, you must go do this. So here I am, all these happy, smiling people. And there I am hating life as they do a story about this kid who synthesized over 100 molecules that never existed, that put atoms in unique geometries that no one ever existed. And I'm reading this thing and I say, I'm a chemist. How did that happen? Next thing you know, I find myself at Princeton University doing cancer chemotherapy, work with Professor E.C. Taylor, published about 16 papers on the design of a series of antifolate inhibitors, dehydrofolate reductase, thymidylate synthase, GER transformolase inhibitors. Now, a lot of people worked on this project. I played a very small role, but I am the witness to the research disclosure. This work ended up becoming the drug Alimta, sold by the Eli Lilly company, one of the most successful anti-cancer drugs for solid tumors. Just to show how worlds collide, my mom passed away of cancer in 2002. She was receiving the drug that I helped design 15 years earlier that extended her life and helped her, prolong things at least a little. If you come to the Princeton campus in New Jersey, the new chemistry building, the 6-story amazing building, is built entirely from the money that Princeton got from this one drug. So Princeton is pretty happy with this kind of chemistry. This is my research lab in chemistry. My father would not have ever understood what a graduate student was. So I never told him I went to graduate school. I told him that I was an apprentice. And so he came one time and visited me. And in my lab, I'm kind of kidding, but there was a telephone in my lab. And I'm about to graduate with my PhD. I'm now 23 years old, 24 years old, and the phone rings, and it ends up being a corporate officer from the Polaroid Corporation, the instant photography company, Lloyd Taylor. He knows everything about me. He says, John, I remember when you were on Celebrity Magazine. I remember when you spoke at the National Academy. I've read your papers. So he knows everything about me, and he goes, let's have lunch. And so I go and have lunch with him. And at lunch, he offers me the job to lead a chemistry group in exploratory research at the Polaroid Corporation. Now, at this point, I had already accepted 2 positions at universities. I was planning on being a professor of medicinal chemistry in universities. And I told him, I said, no, I'm an academic. I'm going into university. He told me how much he was going to pay me. I said, when do I start? And next thing you know, I'm an industrial chemist at Polaroid, the instant photography company founded by this man named Edwin Land. Edwin Land, only Thomas Edison, my background is Thomas Edison's lab. At this moment in time, only Edwin Land had as many patents as Thomas Edison. In 1974, Edwin Land got the Perkin Medal. How amazing is that? And then, of course, I got it in 2014. So seriously, how amazing can it be? But at Polaroid, very quickly, within 5 or 6 years, I filed about 40 patents and invented a bunch of technologies to holography, medical diagnostics, films and coatings and things like that. But what would a medicinal chemist? I'm a medicinal chemist working at a place like Polaroid. Medicinal chemistry, everything is at room temperature, ambient pressure, aqueous solutions, and industry chemistry, high temperature, high pressure, harsh reagents. And so I'm going, how can I think like a medicinal chemist, but work in the chemical industry, making materials? And so one of the sciences that I invented, one of the things I did is what I call non-covalent derivatization. It would take me 1 hour to explain this. It's essentially taking multi-molecular systems, having them crystallize, and you actually control the properties of a material by the bond angles of the hydrogen bonding, by the lipophilic interactions, by aromatic interactions. And so to control chemical and physical properties, not through covalent making and breaking of bonds, but through non-covalent derivatization. I am so crazy about this technology. My license plate in Massachusetts is NCD for non-covalent derivatization. So I'm really crazy about this. And I filed my first patent in 1991. It took until 2011, but now the FDA has a guideline for this in the pharmaceutical industry. And so I invented this, but this was in 1988, 1989. This was just completely new science. There was no textbooks, there were no journals, there was nothing about it. And Polaroid wanted to go to large-scale manufacturing with this invention. To get EPA approval, back then, around 1990, you had to get what was called a low volume exemption, a pre-manufacturing notification from the Environmental Protection Agency. So we filled out all the paperwork for one of my inventions, sent it to Washington, D.C., and we waited and we waited. And the EPA did not know what to do with it because it was new chemistry. They said, we don't know how to think about this. What is non-covalent derivatization? This is crazy. Small particles, molecular complexes, IUI. They didn't know what I was talking about. So Polaroid put me on an airplane and sent me to Washington, D.C. to explain my invention. So I'm nervous. This is like one of the first times in my life I've been on an airplane. All right. I've got a briefcase of overhead transparencies. I'm at the office of the EPA in Washington, D.C. I'm going to see the head of the Office of Pollution Prevention and Toxics, this guy, Paul Anastas. Wait a minute. I know this guy. Remember when I was a music major in the chemistry lab and the professor asked the person next to me to go into research? It was him. I've known him since I was 11 years old. In fact, at the time I was playing in a jazz band with his older brother. This is Paul's older brother, Nick. This is me. I am Paul's age. This is my older brother, Matthew. That's the same age as his older brother. We've been friends. The family have been friends, like I said, since 11, 12 years old. This guy here playing the guitar in this band, if you ever go to Las Vegas, the guy who plays Rod Stewart in Legends of Rock is this guy here, very famous, but has nothing to do with this talk. I just thought it was cool and I'd tell you. So anyways, I said to Paul, wait a minute. Polaroid has been manufacturing this process, multi-step synthesis, all these solvents, all this energy, all these hazardous reagents. And I've invented this aqueous, room temperature, non-toxic process. And the EPA is making it difficult, not because of toxicity, not because of environmental issues, but just because it's different. Isn't anything better for humans or the environment going to, by definition, be different? And if the EPA says it is easier if you continue to do what you've always done, and we're going to make it very difficult for you to do anything different, isn't that working against the dream of having a safe and sustainable future? Shouldn't they instead be promoting things that are good? But here's the interesting thing. What does good mean? So this is like 1991, 1992, and we're saying, well, what does good mean? Is it non-toxic? Is it biodegradable? Is it is it, use solvents? Is it hazardous? Is it flammable? What do we mean when we talk about good? At exactly this time, so I'm at the EPA, my career at Polaroid is going great. I have gotten many promotions. I've got all these awards. Everything wonderful is happening to me. My head is this big. I am the greatest chemist who ever lived. I am so, proud of myself. And disaster hits again. This time, my 2-year-old son, John, dies of a birth defect. My son, John, was born with a disease called biliary atresia, where his liver was not attached to his intestines. He got surgery at birth to keep him alive. And at 2 years old, at exactly the time that I'm having conversations at the EPA, he dies. And I'm lying in bed the night of my son's funeral. And I ask myself, I wonder if something I touched in the chemistry lab caused my son's birth defect. I wonder if something I got an award for somehow caused my son's disease. I didn't think I was this greatest chemist who ever lived. There's something wrong. I don't know the answer to the question. It's not the answer that bothered me. It was the fact that I couldn't answer the question. All right, I'm familiar at this time. This book just came out, Our Stolen Future. I'm start looking. At this point in my career, I've synthesized over 2,500 new molecules, not repeat syntheses, brand new molecules. And I realized 4 years of undergraduate, 4 years of graduate school, I never had a class on toxicology. Never had a class on what makes a molecule biodegradable. Never had a class about laws and policies of doing things. How could I be such a successful industrial chemist and have really no idea about how do people look at the negative aspects of chemistry? Now I'm looking and there's all kinds of information, higher incidence of certain types of tumors, professional chemists have more cancer, all these reports. And yet 8 years of education, never had a seminar, never had a class, never had a course, never had a discussion, certainly didn't have any tests on how to relate molecular structure to the potential harm it could cause. Every year in the United States alone, not the world, just the United States, 15,000 people become chemists undergraduate every year. 3,000 masters, 3,000 doctoral degrees. In 2004, more women started to become chemists than men. What could be more important to the field of chemistry than some training in how to anticipate harm to humans in the environment when you become a chemist? And yet, to get a degree in chemistry, no universities require any demonstration of knowledge that you know anything about the potential harm. Think about that. Doctors, lawyers, teachers, nurses, architects, engineers, they must maintain a license and take tests, not to show that they are skilled, but because that they show that they're up to date on the things that could go wrong. There's no such thing in chemistry. So why are there red dyes that cause cancer? Why are there additives that cause birth defects? Why are there molecules that are in? This isn't some epic battle of good and evil. People want to say, oh, industry is evil, chemistry is evil. No, it's not Darth Vader, Luke Skywalker. It is some strange artifact of our history that for some strange reason, not because of good and evil or anything, just for some strange reason, the curriculum of chemistry, the classes that we teach, we never added a class on how do you anticipate whether something can hurt humans or the environment. Now, we could be despairing and say, oh my God, this is terrible. Or we could say, maybe this is the path to a better future. And so Paul and Astis and I, we realized we don't want a political movement. We don't want, some social movement. When you learn chemistry, there's a textbook called Analytical Chemistry. When you learn chemistry, there's a textbook called Physical Chemistry. When you learn chemistry, there's a textbook called Inorganic Chemistry. I would argue there is no such thing as an organic chemist. There is no such thing as a physical chemist, because if you're going to function as a human being, you do a little bit of organic, you do a little bit of physical, you do a little bit of inorganic, and you just kind of define yourself narrow, but actually it's meaningless. Chemists do everything. All right. And so I said, science, we need a science. And what do sciences have? Journals, textbooks, classes, conferences, workshops. And so like analytical and physical and inorganic, there needs to be this thing called green chemistry. And so Paul Anastas and I, we wrote this book. Had I thought anyone was ever going to read this book, we would have written a better book. It's been translated into over 15 different languages. I've been to over 65 countries in the last several years, meeting presidents and prime ministers and cutting ribbons and giving talks. But green chemistry simply is just the utilization of a set of principles that reduce or eliminate the use or generation of hazardous substances in the design, manufacturing, and applications of chemical products. Green chemistry isn't about cleaning up afterwards. Green chemistry isn't about avoiding doing things. Green chemistry is inventing new things that do that. And it's based on these 12 principles of green chemistry. Now, these aren't words from God or something like this. After many, many years of doing this, Paul Anastas and I, we said, how can we categorize this to make green chemistry very understandable? So there's the definition, and then here are 12 principles that expand. These don't speak to a marketing person. These don't speak to someone who's not a chemist. Okay, we're talking about activation energies. We're talking about catalysts. We're talking about protecting groups. No one outside of chemistry is going to really understand the 12 principles of green chemistry. And that's the point. This isn't for the world. This isn't for everyone. Green chemistry is for people who do chemistry. So when you think of all the things in sustainability, the one little part that is what chemists do, in my opinion, is the green chemistry part. Okay. And so from my perspective, for green chemistry to work, it isn't a philosophical thing. It must actively succeed in society. So while green chemistry must have some environmental benefit or some benefit for human health, that's not enough. It has to work as good or better than something that people are already using. People are not going to say, oh, this works, this doesn't work, but it's green, so I'll use that. Who's going to do that? And it has to have the right cost. If it's too expensive and only rich people can use it, that's not fair. So for something to be green chemistry, it must work better than any other technology. It must cost the right cost. And then, oh, by the way, it's also better for human health and the environment. So for green chemistry is not removing something from the field of chemistry. It's keeping everything that is in the field of chemistry and now adding one more textbook that talks about what are the possible harms to human and the environment. Now, the field of chemistry has been going on for 200 and something years. Okay, it's a very long history. Green chemistry has only been around for a short time. There is no magic green button. We can't snap our fingers and tomorrow make everything green. This is going to take decades and decades. So to do green chemistry, we can't insist that tomorrow everything be green. It's going to take us a long time to invent things. So in my opinion, the biggest barrier to the future for green chemistry is not getting people to want to do it. Who wouldn't want something that works better, costs better, and oh, by the way, is more healthy for humans and the planet? Of course they would. But the question is, do they exist? So in my opinion, the biggest barrier is not getting people to want it, but to invent it in the first place. And so at the height of my career at Polaroid, I decided to leave and go to the University of Massachusetts, chemistry in Boston, plastics engineering in Lowell, and become a professor and start the world's first PhD program in green chemistry. Everything that's in a normal chemistry program, but added additional classes, one in law and policy, one in toxicology, one in environmental mechanisms. Over the next 12 years, over 150 students passed through this program. The average time it took one of those students to get a job in industry, 2 days. The longest any student spent looking for a job was 2 weeks because she turned down her first 6 job offers. I have been out of academia now for 12, 13 years. I still get emails and phone calls every day. John, do you have any students that we can hire? Because they know world-class chemistry. They know how to solve problems. But on top of that, they have some understanding of impacts on human health and the environment. Because in my opinion, of all the products that we have in our society, the ceiling tiles, the carpeting, the textiles, the electronics, the foods, maybe 10% are truly benign. 90% of everything needs maybe a little improvement or a lot of improvement, but there's somebody shaking their fist angry about 90% of the things that we do. If you do a Google search and you say, is there anything out there that could help me? Maybe 20-25% of the time, there might be something here. But right now in 2022, it is my estimate that 65% of the technologies or more have not been invented yet. Think about that. What more important thing could a person dedicate their life to? Can you imagine an undergraduate student working in a lab, inventing a technology to take a traditional technology and making it a little greener? Hundreds of thousands of people they will never meet will not be exposed to some hazardous material because of the work they did. Some ecosystem somewhere will not have some contamination because of the work they did. Why, oh my goodness, what would you want to do? How would you rather spend your life solving problems and doing amazing science at the same time? Because where do products come from? We take molecules, we turn them into materials. We call that basic research. We turn materials into components. We call that applied research. When we turn components into devices, we call that development. When we do a lot of that, we call that manufacturing. If you're in the business of manufacturing, you need to worry about performance, cost, society. Hey, that was my definition of green chemistry. There's nothing new. It's just when we look at the process of inventing and in the industry, we've got to take the environment. Where did those molecules come from? Are they depleting or are they renewable? At the end of a product's life, is it going to be biodegradable or is it going to be persistent? When we manufacture it, when we sell it, when we use it, who is the only person, the single only person who can change this? The inventor, the first chemist who invents that technology. Because once it's on the store, it's already out there. So now we have to worry about cleaning it up and protecting people. And so this is an amazing opportunity for people to really make a difference in the world. This isn't the birth of ethics. People who have never heard of green chemistry, of course they care about human health and the environment. Everyone, no one is out there saying, I want to make toxic materials. Green chemistry is not saying, hey, we should care. I believe chemists have always cared. That's not the point. But how did we deal with it? How did we deal with the fact that some chemicals are toxic? What we did is we said, okay, chemistry has to be toxic. So we must create engineering ways to protect us. We'll wear gloves to protect our skin. We'll wear masks to protect our lungs. We'll wear goggles to protect our eyes. We'll install filters and scrubbers and smokestacks to protect the air, the land, and the sea. Yes, chemistry has to be dangerous, but it's okay because we're going to protect people by controlling exposure. Now, the interesting thing is that first slide, when I put all those headlines from newspapers of all these disasters, if you ask the people the day before, they would all say, no, it's okay. We've got gloves, we've got masks, but accidents happen. So the revolution that is green chemistry is saying, yes, we always are going to have to protect people by controlling exposure. But now the field of toxicology, the field of environmental health sciences has expanded. We now mechanistically understand, not a lot, but a little, on what makes a molecule a carcinogen, what makes a molecule an endocrine disruptor, what makes a molecule biodegradable. But if the people who invent chemistry don't have any training on what makes a molecule a carcinogen, what makes a molecule a biodegradable thing, what contributes to global climate change, how can they invent alternatives? So the dream of green chemistry is to move to a focus, and this is going to take decades, it's going to take 50, 60, 70 years. It's not going to happen overnight. But how can we move from an exposure to making the molecules just a little better? Because a company, if you have to work with a toxic material, cost a lot more money to store, a lot more money to transport, the treat, the disposal, regulations, liabilities, worker health and safety, all things are more expensive. So once the green chemistry book came out, almost every company in the world started green chemistry programs because it just makes money sense. You can save a lot of money if you do green chemistry. Universities, not so much. But companies immediately started doing green chemistry because it just makes sense. All right. So what is the difference between green chemistry and sustainable chemistry? I'm very sad because green chemistry has a book. It is now 1998 is when the book came out. It has a single sentence definition. It has 12 principles. How can anyone possibly be confused about what green chemistry is unless they haven't read the book? Now, if I don't read a book on astronomy, I may not know what astronomy is. That doesn't mean astronomy should change. It means maybe I should read the book on astronomy. When I talk about green chemistry, it would be helpful if people actually knew what it was. And so what green chemistry is different than sustainable, and this is really important to me that you understand this. Sustainability is a huge concept. Any word, you think of any word and you can put sustainable beside it. Sustainable economics, sustainable agriculture, sustainable education, sustainable business, sustainable chemistry, sustainable engineering. No word does not work. So sustainability is huge, but sustainable chemistry is also pretty big and not really defined. There's not really a definition for sustainable chemistry, unfortunately. No one wrote that defining book. But to me, sustainable chemistry, chemicals policy, governments do sustainable chemistry, remediation technology. If there is a spill and you pick it up, that's sustainable chemistry. Mitigating exposure, controlling exposure. Green chemistry to me is a part of sustainable chemistry. Water purification, alternative energy, others. Green chemistry to me is the part of sustainable chemistry where you just look at the molecules, not what the molecules do, but what the molecules are. Solar energy, we need alternative energy. Alternative energy is critical for sustainability. But if we use toxic materials to make our solar panel, in 20 years, what do we do with those old solar panels? If we use, epichlorohydrin and formaldehyde to make membranes for water filtration, we may purify water, but we're still making other things. So what green chemistry says is, right now, let's just look at what are the building blocks? What are the solvents, the catalysts, the feedstocks, the toxicity, the persistence, the energy? Hey, there are 12 principles. Let's use these 12 principles. So green chemistry is that smaller part of sustainable chemistry, which is a smaller part of sustainability that chemists do. And this, in my opinion, this is the most important thing. When people say, oh my God, I want to do something important. Say, well, you should be the best you should be. Well, yeah, of course you should try to be the best you should be. But more importantly, you should ask yourself, what can you do that other people can't do? If we're chemists, we do chemistry, and we should use chemistry to solve these problems, not stop being a chemist and go do something else. Oh my God, who's going to invent these new solutions? So green chemistry is the part that the chemists do to invent the new future solutions to these problems. Okay, so from my perspective, the chemical enterprises have a huge toolbox. We have all these draws. One draw has all the carbon-carbon bond forming reactions. One draw has oxidations, reductions. If we can conceive of a molecule, we can probably make it. But if we consider a green chemistry toolbox where there's transformations are non-toxic, environmentally benign, not regulated, this green chemistry toolbox is 90% empty. I strongly believe that a person will open the green chemistry toolbox first. Better performance, better cost, better for the environment. A company will likely, if they're smart, open it up first. Governments will go there first. But 90% of the time, the draw is going to be empty. So the challenge to us in chemistry is to work as fast and as hard as we can to fill this toolbox. It will take 50 years or more to substantially do this. But if we're not teaching our scientists, if we're not teaching our chemists what makes molecules toxic, what makes molecules hazardous, how are we going to fill any of these things other than by luck? All right. So in 2007, I loved my academic career. I loved being a professor, but I wanted to invent more. I wanted to focus more on invention. So I met this man, Jim Babcock, and started the Warner Babcock Institute for Green Chemistry. Call this an invention factory. And using the tools of green chemistry, within 6 or 7 years, filed over 300 patents. Okay, composites and textiles, adhesives and coatings, cosmetics and personal care, infrastructure and construction, electronics, imaging systems, water technologies, pharmaceuticals. Worked all of these companies here. They have published patents that have my name on it. So these are viewable in the public. There's a lot more that aren't visible, but all these companies, the Warner Babcock Institute, we invented solutions using green chemistry. All right, we spun out, my investor started a company, collaborated these companies here. And I want to share with you very quickly some descriptions of these technologies so you really have a sense of what green chemistry is and the power of green chemistry. So I call this the technology greenhouse, where I go from ideas to prototypes, to technologies that make it to the real world, just like a seed grows. And I have this greenhouse of technologies. One of them is this asphalt pavement. Okay, in the United States, there is 1 billion miles of asphalt roads. The sun and the air oxidize the surface of the asphalt, making it brittle and crack and hard. So 10% of all roads in the United States, in the world, are repaved every year, 10%. Now that brittle, hard asphalt that has been oxidized is too brittle to use again. Maybe they'll take 5–10% and put it in the new road, but 90% of it goes to some landfill. I said, why can't I invent a catalyst using green chemistry to reverse that damage? And so I made the system with my team. I went to, and I dug up my own driveway. So this is my home. In 2013, I dug up my own driveway. I went to an asphalt plant, took my old asphalt, put my additive in, mixed it up. 2 big dump trucks came back to my house. The men were laughing at me. They were saying, John, you're an idiot. It's way too cold. The day I did it was -8 degrees. I had over 70% recycled material. They said, we're going to open the back of this truck. A big hockey puck's going to fall on your front lawn. I actually had someone from the state of Massachusetts Department of Transportation there with a clipboard watching this. I go, okay, go do it. They open up the dump trucks. It comes out, they jump on their bulldozers. It worked beautiful. It's actually better than the initial technology. And so within 14 months of an idea in my head, we created a company called Collaborative Aggregates. And there are 2 products that are sold in the United States, Delta S and Delta Mist. Delta S is an additive. Delta Mist is a spray coat that allows you to use up to 100% in some cases, recycled asphalt, lower temperature, non-toxic, environmentally benign. 14 months from idea to a commercial product. Another example is photovoltaics. I love the artist M.C. Escher. Escher, this is a famous drawing by Escher. There's fish on the bottom and birds in the sky, but it's kind of an optical illusion. When do the birds stop being birds? When do the fish stop being fish? It's kind of a blurry interface. Interestingly enough, in nature, most interfaces are blurry. Okay, when an electron travels across the mitochondrial matrix, it has to take many little steps. So I said, can I invent a semiconductor that slowly turns into a chromophore? The chromophore slowly turns into the electrolyte. And we made solar energy devices that are the highest performing dye-sensitized solar cells in history. We quickly started a company called Ambient Photonics, and we're in pilot manufacturing. This isn't for outdoor use. If you have this on the back of your cell phone, you never charge the phone ever again. If you have it on an electronic device like a mouse or a sensor in your home that you have to change the batteries, you don't have to plug it in. Ambient photons, tiny amounts of light are enough to make this work because it's so efficient. This, from an idea in my head to starting a company, was 18 months. Next example is in pharmaceuticals. This molecule here is totally insoluble. You have to take DMSO and surfactants and apply it to animals, but it does work to do a lot of neurological damage. But you could never use this in a human because DMSO surfactant's not good. And so using non-covalent derivatization, that stuff I talked about earlier, was able to make a form of this drug that essentially not only is more bioavailable, but crosses the blood-brain barrier. And very quickly, we got into clinical trials. It's now, this is an old slide, it's in phase 3, finishing phase 3 clinical trials for ALS already, the Michael J. Fox Foundation, Melbourne. So this, making a drug more bioavailable and cross the blood-brain barrier using green chemistry, again, was about 12, 13 months. The last example I have here is hairprint. All right, this thing here. One day I'm looking at an insect and I'm saying, gee, an insect, when it gets bigger, it sheds its exoskeleton. And over the course of a couple hours, it turns hard and black. That's something in nature that goes from white to black. People color their hair. And so I said, could I make a hair color with this? And so it's a terracinase oxidative cascade. I found a bean called velvet bean. I can extract, I don't grind up dead bugs. I get this oxidative cascade out of a velvet bean. I get some gray hair, put it in it, it colors the hair. Not only does it color it, but it restores the human pigment. This isn't a paint. I'm the grayest person in my building. I put it in my hair. It goes back exactly the color my hair was before I went gray. Woman with black hair, it makes black. Someone with brown hair goes brown. This is the same chemistry, reconnects the human process of making hair color and restores the human pigment. It doesn't wash out. It doesn't fade out. It really is back to your normal hair. Just like you have a fingerprint, you have a hairprint. And so this company has been on the market now for over 5 years. It took maybe 18 months from an idea to inventing and starting this company using green chemistry. And then the last example, sorry, I got one more. In 2015, I found myself on the center stage of the United Nations General Assembly. 2 weeks earlier, 14 days earlier, this cable television show called Whale Wars called me up. They had confiscated 75 tons of ocean trash, an illegal fishing net. They had 2 weeks. We were going to the United Nations. They said, John, can you take out the nylon from the polypropylene? Can you pull out the heavy metals? Can you pull out the pigment? Can you extrude it to a certain size? I didn't have the right extruder, so we built the extruder and within 10 days sent spools of this material to Adidas in Germany. And standing on the center stage of the United Nations General Assembly, guy from the board of directors of Adidas holding up the 2016 running shoe made out of ocean plastics. That was invented using green chemistry in 14 days. Okay, so when people say, oh, green chemistry, it's a bunch of handcuffs, it slows me down. I don't feel that I'm being slow here. The point here is that green chemistry isn't something that hinders creativity, it boosts creativity. And it also addresses issues when you commercialize because you've anticipated regulations, you've anticipated scale-up issues. So the point of green chemistry is I'm no smarter than anyone else. My team is no better. What makes us so efficient is the fact that we do green chemistry. But what worries me is we still have 65% to do. Who's going to invent the rest? And that's why I hope people who are listening to me right now, if you're not already dedicated to this, you seriously consider it. And so what I feel is the most important thing that I'm part of is actually beyond benign. It's a nonprofit run by my wife, Dr. Amy Cannon, brilliant genius, who came up with this concept. And one of the programs that she does is called the Green Chemistry Commitment, where she helps universities find ways to bring green chemistry into their curriculum. As of right now, almost 100 universities worldwide have signed the Green Chemistry Commitment. We've got a long way to go, but I am super proud to say that 3 universities in Brazil are signers of the Green Chemistry Commitment. We got a long way to go. I'm hoping that we got a lot more signers in Brazil and other places. And if anyone is interested and wants to learn more about how to work with Beyond Benign to bring green chemistry into the curriculum, this is their website. I urge you to do this. I hope that this presentation was useful for you to kind of give a shape of what green chemistry is, how important it is to the field of chemistry, and really to the future of our children and our children's children. So thank you for listening to me, and I hope this was useful. Thank you.
Thank you very much, John. It was an amazing, it's so inspiring conference. It's really fantastic. Thanks for sharing a little bit of your fantastic journey. We realized that your life story is mixed with your professional career. It's really fantastic. Thank you very much. Do you think so many important questions to think about the relationship between science and the arts in the beginning of our talk? This is so amazing, about the importance of good professors, of professors that really see and understand the difference between the students. And these are so many important questions to think about. Thank you very much. We have some questions by the audience, but I would just, in the beginning, before to pass the questions from the audience, I'd like to make one personal question. You put the green chemistry field in its right place, because people usually consider a subfield of chemistry, and this is not correct.
Right.
The green chemistry concepts should be inside of the chemistry. It's the beginning of the thing for the chemical. I'd like to know, how do you feel that this green chemistry field have been developing in the world nowadays? I mean, do you believe that this jargon, green chemistry, has been used in the same way as he was designed by you, or it has been, I don't know, like...
That's a very, very important question. Thank you. And so yes, I use the title of my talk, "The Missing Elements," because I'm just suggesting, just like the periodic table, we discover new elements. You know, there was a time, I'm sure, when universities didn't teach inorganic chemistry, and they said, hey, we should add inorganic chemistry. The history of chemistry has been evolving in different parts. As we learn more about the science, the field changes. And so I don't see green chemistry as replacing anything in chemistry. It's just another added component. It makes our job harder. It does not make our job easier. But who goes into chemistry because they think it's easy, you know? And so when I look at how the world has reacted, I put it in 2 categories. You know, there are the people who understand and the people who don't understand. Now, when someone doesn't understand, they either truly don't understand or they intentionally don't understand. And so if all companies, you figure every major multinational company has a sustainability program. They're doing many things. They pay some company to recycle. They pay some company. So many companies are doing sustainability, but most companies are not doing green chemistry. And the way that my diagnosis is really simple. If a company has a training every 2 years to teach their scientists what are the latest that we know about ocean plastics, what is the latest science about global climate change, what have we learned about carcinogens. If a company is committed to making sure their inventors are constantly staying up to date with that, they're doing green chemistry. If instead they're doing marketing and they just say, oh, look at how wonderful it is, then they may not be. And so to me, it's green chemistry is not about as much the molecules as it is about the people. I trust and believe in people. If people have training, they will do the right thing. But if they don't have the training, all the laws, all the policies, all the PR press releases in the world don't make it, if I watch people run the marathon, that doesn't make me being able to run a marathon. All right. You have to train, you have to learn. There are things we have to do to learn. And so because people who are already graduated from the universities are done, companies have to have, all I think it should be like an eight-hour training every 2 years. What are the latest things? I would love it to be longer, but I'm realistic. I understand companies are busy and they don't have a lot of time. So as far as I'm concerned, if every 2 years, if a company committed that every 2 years, they're going to make sure that all the scientists, all the inventors have some green chemistry training, then they do green chemistry. Now, sometimes there are two types of greenwashing. One type of greenwashing is a lie. It is not better. It is just they are lying. In that case, we must say, hey, that is not true. However, if they exaggerate, if a company, a CEO of a company says, oh, look at this is more sustainable, this is wonderful, and they're exaggerating, I think we should be a little bit more humble and still applaud and thank them, because if we throw stones and we yell at them because it's not enough, and they make the decision that this is just too much, I can't make these people ever happy, I might as well do nothing, we lose. So if we celebrate and they say, wow, look at all the celebration, the next thing will be better and the next thing will be, but if we kill people and stop them because it's not good enough, who among us should be so presumptuous to say, I should decide what is good and what is not good? So I think we need to be more humble and celebrate, because that's how science works. If you make something less toxic and I make something less energetic, a third person may learn from both of us, put that together. But if I am silent and I don't tell people what I've done and you don't tell people what you've done, how does science grow? And so the famous saying, I don't know who first said it, the enemy of the excellent is the perfect. Perfect doesn't exist. If we sit around saying we're not going to do anything unless it's perfect, it means we do nothing. And so we must give each other a break and realize that there's so much work to do. Any advance. Now, in my life, there are 12 principles of green chemistry. I have never worked on a research project that addressed more than, say, 2 or 3 principles at a time. That's just not possible. Science doesn't work that way. You got to look at the mechanism and what's going on and celebrate these. So it's going to take 30, 40, 50, 60 years to make significant advances. And so we need to be patient. We need to realize that small advances in chemistry could be huge advances for the world one day. But if we don't allow those small steps to happen, the big steps won't happen.
Perfect, thanks. Let's move on to the questions from the audience. Henrique Pereira Urenha asks you, Professor Warner, do you believe that the synthesis laboratory will be substituted by use of natural organisms, which would produce the substance of interest for us?
Mm-hmm. So I, at this point in my career, have chosen to take a job at the company Zymergen. Zymergen is a synthetic biology company. Here I am, a synthetic organic chemist who has spent my life with beakers and flasks doing traditional chemistry, now work and senior vice president of chemistry for Zymergen, a biology company that is doing fermentation to make molecules. I feel that that is a very important part of the future, because when I have invented things that did not become commercialized, it's usually because the molecule I wanted to work with was too complicated and the synthesis was too expensive. Biology changes the rules. Sometimes molecules in biology that I, as a synthetic organic chemist, say I would never want to make, it's a very simple molecule for that. And so it's at the very beginning, we got a lot of work to do, but if we're going to expand the tools of chemistry to really address new things, one of the most important frontiers, in my opinion, is understanding fermentation technologies and not making ethanol and butanol. That's important, but I'm talking really complicated molecules, dyes, plasticizers, things like that, that we're just starting doing.
Next question, Vinicius Bezerra. Dr. Warner, what do you see for the future of technology for prediction of CMR, carcinogenic, mutagenic, protoxy, potential of chemicals? Yeah. How can we improve the in vivo or in silico methods?
Yeah. Very important question. We must continue to do that, but we must always realize that predictive tools, there is no case in science where predictive tools are 100% accurate, okay? If I wanna make a dye, and I wanna make a dye a red color, and I want it to be 540 nanometers, and I want it to be a certain shape, I can draw a molecule, use a computer program, predict what it is, but then when I go in the lab and I make that molecule, I have no serious belief it's going to be exactly what the computer predicted. It helps me. It is a tool to face, but at the end of the day, I have to make the molecule and test it. Predictive tools for carcinogenicity and things like that are in the same place. It helps us prioritize our research, and I do believe in someday in the future, AI, machine learning may get us to a place that's far better than we are today, but I don't expect in my lifetime to not have to make the molecule and do the test. At the end of the day, we still have, there's a dream in the future, and we intuitive people that are in the lab inventing need to be talking with the people designing these programs, not staying separate, expecting them to throw to us a magic tool. We need to collaborate with them to help our intuition to merge with machine learning to improve both of us. So we both have an opportunity to benefit. And someday in the future, I feel it's going to be super important. Today, it's important for us to work on and to develop. It's not at the point where it answers too many questions yet, but it will in the future.
Yes, thank you. Now the question from Juliana Vidal. Hi, John. How do you think students who maybe don't have the support of their departments for this can contribute to spreading and transforming green chemistry education in their universities?
So Beyond Benign, www.beyondbenign. I have to tell you, of the 100 signers, most started with a student group. The student group starts doing it, and sometimes the faculty go, oh, that's so silly. And the students get more serious, and then the faculty say, what are these kids talking about? And then they keep going, and next thing you know, finally, the faculty actually go and listen to a talk on green chemistry or pick up the book, and they say, oh my God, this is really interesting. And next thing you know, they sign the commitment. But more often than not, it's the students that propel change. And don't underestimate the power of students in influencing the future of chemistry, because you are the future of chemistry. The faculty are not the future, you are. And so don't underestimate that. If you say, and it's one of those things, once you understand it, how can a university really, from my perspective, how can a university say, no, we should not do this? That confounds me more. You know, I understand it's difficult. You know, it's hard to change the education. Faculty is so busy doing so many things, but what in the world could be more important to say, no, we don't have time, we should not put this in the curriculum? That to me is crazy, but I understand people look at the world in different ways. I am 100% confident there will be a day in the future where we will laugh at the time when every university didn't do green chemistry. And we'll say, can you believe there was a time when we didn't do it? But that time will happen regardless. That momentum is happening. The next generation, the students understand this and will make it happen. The point here is, how long is it going to take? You know, and how long do we have?
Question from our president, Professor Romeo. Thank you for this inspiring webinar, John. As you pointed out, the design of the chemical is key. What do you recommend as fundamental steps in becoming a good, productive chemical designer?
When people ask me, what is the secret of how do I have all these patents? The first thing I say is it's because I have a lot of good people helping me. But the other thing is that innovation, if I have an idea, all right, and I ask 10 people, here are my 2 ideas. And one idea, everyone says, oh, that's a good idea, you should go do it. And one idea, everybody says, oh, that's crazy, that'll never work. If you go in the future and you say both worked, which one did you get funding for? The one everybody said was going to work. Which one did you not get funding for? The one that everyone said wouldn't work. By definition, which was more innovative? The one that people said won't work. So if you want people to love you and say, oh, your ideas are great, your ideas are wonderful, you'll probably only be able to do incremental work. If you want to truly change the world, you're going to have to take risks. You're going to have to say, yes, this is difficult, but into it and believe in yourself. That you do, if you can imagine something and you are trained well in science, you have to be a good chemist. There's no substituting really understanding chemistry. So if you really understand chemistry, and you don't have to just do things people did yesterday. If someone did methyl and you say, I'm going to do ethyl, and someone did ethyl and I'm going to do propyl, that's not really what the world needs. You need to go way out there and say, you need to be brave. You need to be courageous, and you got to be okay with sometimes looking funny, because for everything that works, there's going to be things that don't work. And so courage and conviction. So number one, pick a science that you love. If you love catalysis, do catalysis. If you love polymers, do polymers. If you love whatever it is that you love, do that. If your environment, if your university has a great green chemistry program, use that. If your university doesn't have a green chemistry program, well, take that responsibility upon yourself. Learn the chemistry first, become an excellent chemist, and take responsibility yourself for bringing the green chemistry in. If your university isn't, your success will change the university. Your university will not make you successful. You will make the university successful.
Okay, so now our last question from Bruno Gabriel Rodrigues. How this knowledge can be applied in agricultural products, such as pesticides, for example, since the chemical properties are very sensible in their applicability?
Mm-hmm. So obviously we need a lot of innovation. In the field where a molecule is designed to kill something in nature, there is a fundamental issue there that we are designing a molecule to kill something. And so where green chemistry comes into place, when you look at pesticides, if a perfect pesticide existed that only touched the organism that you're after, did not touch anything else, did not spread, did not get into the waters, did not kill other organisms, it would be wonderful. But that doesn't exist yet. And so green chemistry is, how do we reduce the dosage, increase the efficacy, make it more targeted? And now here's the revolution. In my opinion, we need to look at persistence. Okay, for the history of pesticides, people do a thermal stability test. If a pesticide is not thermally stable, you'll have no shelf life. If you have no shelf life, how do you sell it? However, if you use non-covalent derivatization, you have a pesticide that is unstable and you temporarily stabilize it with non-covalent derivatization. Then when you apply it to the field, it separates. And once that non-covalent derivative separates, you have a thermally unstable. If that decomposition goes to safe byproducts, you have no persistence. You have planned timing. We have to look at how we can create molecules that have biological activity when we want it to, but then turn that biological activity off when we don't. That's how we can protect the neighboring farms, the drinking water, and the environment. But that is science fiction right now. We don't have those technologies. I'm personally working on some of them, but it's going to be a while before we figure that out. But that's what we need to do, or find things that are already in nature. You know, that's not perfect, because even changing balances of natural materials causes eutrophication, causes environmental damage. So just because something's from nature doesn't necessarily mean it's going to solve all of our environmental problems, but it's a good start.
Okay, thank you very much again, John. We don't have more questions. It was really an amazing experience hearing about your experience, about your professional story, and I'm sure that this conference will inspire a lot of Brazilian new students and professionals, and I hope in brief we can meet together in some place. And thank you again. Thanks for the people from the audience. And we are looking forward to the next SBQ webinar. And bye. Have everyone a very nice weekend. Thank you very much. Bye-bye. Bye, John.
Bye-bye. Thank you.